we are discussing the implementation of state graphs. So, go through a state table and from there to a combination logic which will drive the flip flops, so that the state transitions will occur as per the state graph. So, basically any circuit can be represented as a state graph in which several states are defined, and each state is determined by the next, each state, the transition to from one state to the next state is determined by the present state as well as the input variables. Now, as an example, we took the case of a counter with no external input, a counter which is not a sequential counter, which is an arbitrary sequence counter at 6 states 0 to 5, S0, S1, S2, S3, S4, S5, and it had to go through this sequence. And since there are no external inputs, it is assumed that each state, the circuit remains in each state for one clock period. At the end of that clock period, it goes to the next state. So, what we have to decide is, from this state to this state transition, what inputs should be given to the flip flops. There are 6 states, so there requires a maximum of 3 flip flops. With 3 flip flops, you can have 8 states, and these 3 flip flops have to be steered from state to state based on the present state values and the sequence required. The first exercise we did was using D flip flops, where the next state variable is the same as the D input. But if you want a JK flip flop as an flip flop to be used, we need to find out what J and what K has to be given for each flip flop in order to change it from a given present state to a given next state. We introduce a concept called excitation table. If you take the JK flip flop, this is the table of behavior of the flip flop. It is called characteristic table. The flip flop behaves in a memory state, reset state, set state and toggle state. Given the input J and K and a value of Q, what will be the next value of Q? This is called a characteristic table, or similar to a truth table. But what we want is an inverse of this. What we want is, if a flip flop stays in a particular state and if it has to go to the next state, what inputs have to be given to J and what input to be given to K in order to steer a flip flop from a given present state to a given next state. So, this is an inverse table. Of course, you can, all the information is here in this table. I have to rewrite it in a way such that what values of J and K will steer the flip flop from a given present state to a given next state. There are only 2 present states possible, 0 and 1, and 2 next states possible, 1, 0 and 1. So, there are only 4 transitions possible. The present state can be 0, next state can be 0, present state can be 0, next state can be 1, present state can be 1, next state can be 0, present state is 1, next state also can be 1. For each of these 4 transitions, what J and what K will make these possible. Such a table is called an excitation table. How do you excite the flip flop or the inputs to the flip flop? How do you steer the flip flop from state to state? So, that is what we set about doing for a JK flip flop, taking this as the characteristic table of the flip flop. What change of what input values for J and K will make it remain in state 0, will make it go from 0 to 1, will make it go from 1 to 0, make it remain in 1. That can be obtained from here. For example, the present state is 0, the next state is 0. These 2 rows of the truth table are the characteristic table, behavior table. Tell you if the present state is 0 and next state is 0, what inputs are required? Input has to be 0, 0 or 0, 1. J has to be 0, K can be either 0 or 1. If J is 0, and K can be 0 or 1, that means it do not care. a JK flip flop will make a 0 to 0 transition. So, the next is 0 to 1, this is 0 to 1, 0 to 1. These two rows correspond to the transition of a present state 0 to next state 1. Both these cases j is 1, k is 0 here, k is 1 here. So, j has to be 1, k is do not care, which will make a transition of 0 to 1 possible. Next is 1 0, present state is 1, next state is 0, this row and this row. Present state is 1, next state is 0. J is 0 here, 1 here, whereas k is 1 in both cases. So, k has to be 1 necessarily, j can be either 0 or a 1. And finally, 1 to 1 transition is present state is 1 and next state is also 1, will happen if both j and k are 0, or if j is 1 and k is 0. That means j is do not care and k is 0. So, this table is called the excitation table of JK flip flop. So, when you are going to design a steering logic in any state machine which is represented by a state graph, we need to design a combination logic called a steering logic, which will take this circuit from one state to the next, to the next, to the next, as given by the requirement, the sequence required. So, I need to design a steering logic for this flip flop, so that given a present state value, what will be the next state. So, what should be given to the inputs of the flip flop, each of these flip flops, so that next state will be as required, as desired. So, my steering logic will have to necessarily take this information of the excitation information of the flip flops into account before I can write the combinational logic table. This is the combinational logic table, which is also called state table, because it is going from state graph to state table. In the D flip flop we did not have to do this, because D flip flop the output is same as the input, next state is same as the present input. If D is 1, the next state is 1, D is 0, next state is 0. So, it was indirectly done, we did not do explicitly, we did for the next states, we did the map for next state for flip flop A, next state for flip flop B, next state for flip flop C. For the previous example where we used D flip flops, we wrote corner maps for DA, DB, DC, because next state is same as the inputs. It was built into that mechanism. So, we did not have to explicitly draw the excitation table, write the excitation table and then get a steering logic. But a JK flip flop is not the case. In a JK flip flop, I am going to use the same example that we used earlier of this transition 001 to 100 to 011 to 101, 010 to 110 back to 001. This is the transition required from the present state 001 to next state 100. Flip flop A has to change from 0 to 1, B has to remain in 0, C has to change from 1 to 0. So, what excitation JA and KA will I give in the present state 001, so that the next state of this will be 1, next state of this will be 0, next state will be this. For what excitation I will give for JA KA, JB KB, JC KC, so that the next state of A will remain will become 1, next state of B will remain 0, next state of C will become 0 from 1. So, my table has to have that information here, JA KA, JB KB, JC KC, and that will be simplified, and that will be the steering logic now, this combination logic which is going to steer the flip flops from state to state. Earlier we had only DA, DB, DC 3 outputs correspond to 3 present states, and these outputs were directly gotten from the map because D and Q were the same. because the excitation table of a D flip flop is, if you want to draw the excitation, the present state is Q, next state is Q plus, what should be D? It is 0, next state is 0, D has to be 0. Present state is 0, next state is 1, D has to be 1. Only then it will change from 0 to 1. If the present state is 1 and the next state is 0, D has to become 0. Only when D is 0, D plus Q plus will become 0. So, what is the need for writing a table separately, because this is same as Q bar, Q plus. The next state value of Q is the same as the D input required. Because of this nature, I did not have to explicitly tell you about an excitation table for a D flip flop. I directly taken that into account in my table and simplified the table to get the logic. Here I cannot do that. Here it is JA, KA, JB, KC, JB, KB, JC, KC. They are different for each state from transition to transition. So, I have to fill this table with the input values for JA, KA, JB, KB, JC, KC, and then simplify each one of them and draw my steering logic, which will take the flip flops from different states, from each state to a different state as required in the problem. So, let us complete that exercise here. For 0 0 0 and 1 1 1, the states are not defined in our sequence. So, next state is not defined. So, next state information is do not care. For each one of the other things, I need to know that now. The present state is 0, the next state is 0 for A. So, what should be JA, KA? Look at 0 0, 0 0 entry, the JK flip flop, 0 do not care. So, if the present state is 0, next state is 0, I need 0, 0 to 0, 0 do not care. What? Oh, I need to do that. Okay, I think you are right. I need to actually write the next states to not to make it. So, I will write here the next states, because otherwise I am going to make mistakes as I did just now. Next state value is not defined for the first one. For 0 0 1, the next state is 1 0 0. So, I have to see this state and this state. You are right. Present state value is of A is 0, next state value of A is 1. What transition should happen? Then what? 0 1 0, what is the next state? 1 1 0. 0 1 1, next state is 1 0 1. 1 0 0, next state is 0 1 1. 0 1 0, 1 0 0, 1 0 1, the next state is 0 1 0. 1 1 0, next state is 0 0 1, and for this state there is no next state defined. Actually, I should have put it here next to this, make it convenient. Since I use the same table from the D flip flop, I just change the inputs from DA, DB, DC to JA, JB, JC, KA, KB, KC. I am putting it here. Actually, it will be nice to write the present state, the next state, this is present state, values of the variables, next state values of the variable A, B, C, this is really A plus, B plus, C plus, right, and then the corresponding inputs, flip flop inputs. This table is also called, is not called state table, is simply from state to state variation. If I write a table for this instead of a diagram, it is called a state table. A table which contains not only the state changes, but also the inputs of the flip flop, such a table is called a transition table. This is the state graph or state map. if I put it in instead of this, if I put it like this, present state 0 0 1, next state is 1 0 0, present state is 1 0 0, next state is 0 1 1. If I write like that, that is, instead of writing a map, I write a graph, I write a table. Such a table is called a state table. A state table where the present state value, the next state value along with the flip flop inputs is given. Such a table is called a transition table. The transition table is required to draw the Karnaugh maps for JA, JB, JA, JB, JC, KA, KB, KC, and in order to get the transition table, I need the excitation table of the given flip flop. In this case, we are using JK flip flop, so I need JK excitation table. If I want to D, I also have present state, next state, and D values, but Q plus is same as D, so we are not writing a separate excitation table and separate transition values. So, next state table alone can help me to design D flip flop steering logic. For D steering D flip flop steering logic, I do not need extra input columns because D and Q are the same. So, I do not write a separate excitation table, I do not write a separate transition table. The next state table can be directly used for Karnaugh maps, but not so for JK flip flops. Okay. So, now we know present state is 0, next state is 1. What should be JA, KA? 1 do not care, 0 1, 0 to 1, again 1 do not care, 0 to 1, again 1 do not care, 1 to 0, do not care 1, 1 to 0, do not care 1. This is for JKA. JBKB, you look at the B value with present state and B value is next state. 0, next state 0, 0 to 0 is 0, do not care. 1 to 1 is do not care 0, 1 to 0 is do not care 1, 0 to 1, 1 do not care, 0 to 1, 1 do not care, 1 to 0, do not care 1. You can see one pattern here, 50% of this minimum, 50% of this rows are do not cares, these 4 are do not cares, these 4 are do not cares, in addition to the do not cares for the next state not defined. Not defined do not cares also there. In addition to them, 50% of the entries will be do not cares. So, our map will be simpler. When you have a lot of do not cares, our maps will be simpler, the hardware will be simpler. So, JAK maps will be very simple compared to the D flip flop maps. So, JC, KC, present state 1, next state is 0, 1 to 0 is do not care 1, 0, 0, 0 do not care, is that right? 1 to 1 do not care 0, 0 to 1, 0 to okay, 1 to 1, 1 to 0, 1 to 0 is do not care 1, 0 to 0, 0 do not care, 1 to 1 is do not care 0, 0 to 1 would be 1 do not care, 1 to 0, this would be do not care 1, 0 to 1 would be 1 do not care. So, you can again see every column at least 4 entries are do not care and more, because more entries than 4 are do not care, because some of them are not defined states. So, there also you have do not care. Even if all the states are defined, there will be 50% of them are do not cares. So, from here the next step is to draw the Karnaugh map for JA, KA, JB, KB, JC, KC, and then draw the steering logic. which is a fairly straightforward affair. So, we will map this J A, do not care 1 1, this is J A map. What is J A? Value of J A 1, all do not cares can be assumed as 1, J A is 1. K A map will be all do not cares, all 1. That is what I meant when I said J A, the J flip flops, JK flip flops, the steering logic will be simpler, even though there are 2 inputs each time, because at least 50% of them are do not cares. So, JB KB maps JB do not care 0, do not care, right. This is JB, KB will be do not care 0 1, so what is JB? This is JB A and JC would be KB will be what? C, K will be C. What? Oh. A plus C. You are right. Then the last set of maps JC and KC. Do not care 0, do not care 1, do not care 1, do not care. This is JC A. KC would be do not care 1, do not care 0, do not care 1. KC would be B bar. So, now JA, KA, JB, KB, JC, KC everything is known. So, this steering logic can be now defined. So, in this case it so happens that J is simply 1, this is 1, JB is A, JC is KB is A plus C, B bar. So, this logic has no, I will rewrite this logic here. Three flip flops, call them A, B, C. Q bar. This flip flop will be called A, this flip flop will be called B, this flip flop will be called C. So, JK, 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 this is called JA. So, JA is 1. So, I will have to connect it to 1. JB is also 1. JB is A. A is here. From here it comes. J is KB, A bar, ARC. A is here, C is here. So, combine it here. This is JC 1, KC is B bar, which is also available here. Simple design. JC A, not 1. So, the logic is, even though we are using 3 flip flops, in the earlier case of D flip flop also we used 3 flip flops, number of gates used there was more than in this case. So, even there are 2 inputs each flip flop, the reduction is so much, the hardware, we are able to use very small number of, only 1 OR gate is extra because all the inverters are available in the flip flops, only 1 extra 2 input OR gate along with the 3 JK flip flops, that will suffice, gives you the entire logic. So, that is in principle the design of sequential circuits or state machines, I want to call that. First, define the various states the machine is expected to be in a circuit. If you do not want to call it a machine, call it a circuit or a system or a subsystem, whatever. Define all the clearly the various states the circuit is supposed to be in, and conditions under which the transition from one state to the next will happen. So, we have to define a logic which will take into account the present state and the inputs, so that the next state inputs will be given. Steering logic is defined as that circuit, the flip flops are steered from one state to the next state as per the requirement, which again takes into account the present states and the inputs, external inputs. The 2 circuits we discussed are very simple circuits. I have taken circuits which does not have an external input. That means every clock cycle the circuit has to change its state. Each state the circuit will remain in only for one duration of the clock, one period of the clock, duration of one clock period, and then it will go to the next state, and then it will go to the next state. Of course, I can complicate this by giving external inputs, then the circuit will depend on the present state, as the steering logic will also take into account the external inputs in addition to the present states. That is the generalized model we drew in the beginning of this module of lectures on state graph implementation. You have external inputs along with the present state inputs, which is taken into account, design the external outputs and the next state outputs. So, you can always modify the state graph with external inputs. Let us draw a simple example of a state graph which will also have external inputs. I think we drew this state graph, similar to state graph in the beginning. Suppose I have 4 states, call this S0, S1, S2, S3. The circuit will go from here to here, something arbitrary. Let us say x is equal to 1. So, x is an external input, So, the circuit will have x external input and 2 flip flops. There are 4 states, so there will be 2 flip flops. Of course, I have to draw the clock here. Remember, the clock is required. Clock has, the flip flops need clock to be steered from state to state. So, this will have 2, will simply have a D flip flops. These are the present state values which are fed back, so that next state values will be obtained along with the clock here. And this x will be, x will 0, it can stay here or it can go here. So, maybe x is 0, it will take here, to x 1 it will remain here. And then in this state, let us say x is equal to 0, x is equal to 1, and let us say x is equal to 0. So, each state you have to make sure that, because x is one input variable, it can take 2 values. For a given state, what are the 2 states, next states corresponding to 2 values of x, you have to say. So, this you have to make sure that every state has 2 arrows going out of it. So, x is equal to 0 arrow, x is equal to 1 arrow, so 0 arrow, x is equal to 1, x is equal to 0, x is equal to 1, x is equal to 0, x is equal to 1. Now, in that case, my state table has been written with 2 inputs for present state and 1 extra input for the external input x. So, my state table will look like, let me define these states arbitrarily as 0 0 state, 0 1 state, 1 0 state, 1 1 state, and I call these state variables x and y or p and q. So, present state variables p and q and input x corresponding to the next state p and q, and let us assume D flip flop. So, next state is the same as D. So, we will not, transition table will be same as the state table. When D flip flops are used, state table is the same as the transition table. If flip flops other than D is used, transition table and flip state table will be different. So, present state p q 0 0, x is 0, 0 0, x is 1, what happens? 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. So, if present state is 0 0, x is 0, it stays in 0 0. Present state is 1, 0 0, input is 1, it goes to next state 0 1. This is how we write the state table for this with an external input. Next, from 0 1, x is 0, it goes to 1 0, x is 1 and remains in 0 1. Yes, this is S0 state, this is S1 state, this is S2 state. In S2, the input is 0, it goes to 0 0, input is 1, it goes to 1 1. From S3, if it is x is 0, it goes to 0 1, input is 1, it goes to 0 0. So, this is the transition table as well as the state table, since we are using D flip flops in this model. This is a D, this is PQ, no? I called it PQ. So, I call this DP for the D of P flip flop, D of Q flip flop, DQ. So, this is same as the DP map, it is also same as DP, this is also same as DQ. So, what will be the logic required? Logic required will have to be, you have to draw corner maps using these 3 inputs p, q and x for p plus, which is same as dp, q plus same as dq, and then get the steering logic. So that circuit will be completed. We will do that here. P plus is equal to dp. Map is one state is p, next state is q, and input is x. So use those values, it becomes 0 0 1 0 0 1 0 0. This is p bar q x bar or p q bar x. Okay. Then for the second map for q plus, which is same as dq, the value should be zero one zero one, 0 1 1 0. So this will have 3 terms. One term is p bar x, this term is q bar x, and this term is p q x bar. So circuit corresponding to that, two flip flops, dp, both are clocked. dp is p bar q x bar. P bar is available, q is available, x bar is of course not available, so x has to be inverted. X is an input, external input. P q bar x. dp p, this is q, x p q bar x, p this is what? P bar. Thank you, thank you. Good. Second expression is p bar x. P is available, X is available, P bar is available, Q bar X, PQ X bar. X bar is available because of this inverter. With D flip flop, even though we have only one input, logic is slightly more complex because of only one input. JK flip flop, because of lots of don't cares, you get reduced logic. So this is a generalized system. I didn't have anything in mind when I wrote this state graph. This is a state graph. This is the transition table, state table as well as the transition table. This is simplification of the transition table. This is the logic diagram using flip flops and gates. Of course, I didn't have anything in mind. I just assumed I had input with circuit with one input and 4 states. 4 states require 2 flip flops. Use 2 flip flops. Those flip flop outputs have to be fed back as input information. So 2 state variables P and Q, 1 external input X. So P, Q, X are the 3 inputs to the steering logic and steering logic. So this could be anything. It could be a traffic light controller, for example. There may be 4 states in which X may be an external input. Based on that, the circuit will change state. As an example, I didn't have anything in mind. I just wrote it arbitrarily. But this tells you how to formulate the problem to start with. First, you have to write given a problem specification, you have to come up with a state table, a state graph. What are the various? First of all, you have to define external inputs and external outputs. What are the external inputs and what are the external outputs? Then you draw a state graph. At that time, you may not be clear about how many states are required. I may not be able to start with the number of states, but I may be able to stay. As I develop this state graph, I may know how many states are required to complete the problem. The circuit has to exist in many states, and from one state to the next state it will go based on some requirements or some specifications. So draw the state graph, include the external inputs and external outputs, decide how many flip flops are required based on the number of states you have, then draw the state table, and depending on the type of flip flops, you go to the transition table. Once you have the transition table, you simplify the transition table using corner maps in order to get to the logic, steering logic combinational part, and then you draw the circuit diagram, and of course you have to wire it and test it. What I have not done in this case, of course, one more modification has to be required, but I have not talked about any outputs. I am assuming outputs are the state variables themselves. So the value of P and Q at any given time is the output I have taken. Earlier example also. Earlier example, I have taken 6 states, A, B, C, no external inputs. Could be a counter, as I said. Even though the counter does not count in a natural sequence, these are 6 states in a counter. At any given time, you look at the values of A, B, C, you know the output. It is a binary counter, a sequential counter, those are the values required. In this case, for example, there may be an external output, we do not know. What is the external input? When say external input X, I may have an external output. So I have to define an output also. How do I define an output in this graph? It is possible to define an output. Output in this state can be something 0, output in this state can be 1. So I may have an output called Z, and the Z can be 0 in certain states, 1 in certain states, right. So I can modify the circuit to have outputs. I did not make it in the beginning to keep the complexity level low, so that gradually we can reduce. So in other words, we now have a tool of, we have studied combinational logic, different implementations. We have studied the basic sequential building block, flip flops, counters, shift registers and so forth. Now we know a mechanism of representing a given system or a subsystem by means of a state graph. Of course, we are assuming it is a sequential circuit. And once you have a state graph, you know how to proceed and implement it in hardware using gates and flip flops. Now we have to do, next step is to, is there any way in which I can use, the logic becomes more and more complex. If the number of states becomes large, and number of gates also become very large. Number of states decide the number of inputs outputs to the these corner maps. So, many terms. So, can we make a simplification of the gate level into higher level of logic? So, we can think of combinational building blocks which are more compact to work with. I would like to have fewer parts, and I have fewer parts, fewer components. I will save less, I will save space on my board, I will save power dissipation and cost also. We will talk about some of those things, how to reduce the combinational logic part from an extensive gate oriented, because these examples are very simple examples. When the examples become more complex, when the number of states becomes large, the number of transitions becomes large, our steering logic becomes very large and extensive. So, is there any way I can simplify the steering logic by using fewer components, fewer parts? That is what we will see next.